And the other thing, which is why you need a fair amount of math background, you should have seen some proofs before and so on, is that we will also focus on analysis. Okay? So we're going to look at how you analyze running times, how you analyze memory usage of algorithms and so on. Okay? And another thing is, we'll always try to prove correctness of the algorithms that we design. Okay? So that's something you might not have seen in all the undergrad classes that you've seen. Okay, so we'll see examples of what that means. But we'll always try to show that what you're actually doing computes the right answer. Okay, so that's, there might be some cases where there is no single right answer, but you might want to just prove that what you came up with actually satisfies some desired properties. Okay, so that's what we will show. So that's what I mean by correct. Alright, and the final thing that we'll look at is, we'll try to understand the limits of efficient algorithms. Okay, so there are some problems, as we will see, for which you cannot hope to have very efficient algorithms. Okay, so given some particular problem, let's say you have some problem that arises in some application, we'd like to understand how efficiently can I hope to solve this problem. Okay, so that's the other kind of question that we will ask in this class. So, any high-level questions so far? By the way, so also another thing I should mention in case it's not clear is that you should feel free to ask, interrupt me and ask questions. Okay? Just raise your hand. Yeah. So, I guess one question you should be asking is what's on the slide, right? So it's what about implementation? Okay, so it is. So apart from the project, this class will not have any kind of programming assignments. You will mostly be asked to come up with algorithms, and you will have to, I'll show you how you write down algorithms. You essentially have to give some kind of pseudocode at a fairly high level. Okay. So it's assumed that you should be able to go back and forth. Okay. So given the algorithm, you should be able to go and code it out. Okay. So that's the assumption. Okay. So. Okay, so sometimes this is not very easy, and this is what the project is for. Okay, so you will actually see some instances where you have some interesting coding to do. Okay, so that's what we do. Okay, so now any questions? How we'll go about things? Is the other TA here? Ashkan. Okay, so maybe we'll go to the TA introduction. Oh, right. So, okay, before the TS, the textbook. So I've started to use a new textbook for this class. This is called The Nature of Computation. It's an excellent book, but it's actually, how many of you have either have access to it or have bought the book? Yeah, a relatively small number, right? Okay. So there should be copies of this in the library. Let me know if you don't have access to it. Okay. So this is not a strictly required textbook, but there will be readings from it which I will assign. And it's good if you are able to do these readings. Okay, so it's not strictly necessary that you have the book. Okay, so it's there will be other material available. So those who have the book would notice that it's not particularly a slim book. It's quite dense. Okay, and it's by design. Okay, so the book has a lot of really great material, and it basically tells you how to think about computation, which I think is really nice. Okay, so that's why I have this book for algorithms. So it's somewhat non-standard choice for algorithms. So yeah, so it's great if you guys have access to it. Okay. And since many of you don't seem to have it, at least for the homework problems and so forth, I will copy paste the problem itself. Okay, so I'll just write the text. Okay, so questions on the textbook? You guys seem quieter than
Yeah. Is there any like books that are a little bit more basic in nature?
Yeah, so there's a couple of other books. I hope I have linked them on the Canvas page for the course. Yeah, so I can check that. Good point. So yeah, while we are here, so this is the Canvas page for the class, and almost everything we do, like course announcements and so on, will happen through this. So there's also a way you can set up notifications on Canvas. So if I send an announcement, you get it by email and stuff. Okay, so figure out how that works and sign up for it. Okay, and homeworks, etc. should be submitted via this thing. There will be an interface through which you can submit. So textbooks, okay. Okay, so I don't have the other textbooks, but there's a standard textbook of Das Gupta, Wazirani and others. So let me just pull it up. So interestingly, the whole textbook is online for if you just search for it. So I don't know if it's supposed to be. Okay, so this is the textbook that. So this is a more basic version. So this does not have everything that we will cover, but it has a good chunk. Okay, so it has at least what we will cover until the midterm in there. Okay, and usually I'll be providing readings. So if you have this and do the readings, that's also fine. Okay, so this is a good textbook. And there's of course a whole bunch of the standard textbooks, like CLR is a standard textbook for algorithms. So I can give more links if you guys need. Alright. So let's get back. Alright, so the logistics, as I was saying, so everything by way of announcements, lecture videos, etc. Will be uploaded on Canvas. So in case you didn't know, every lecture is recorded, so that's what my TA here is doing. So seems to be doing a good job of focusing and stuff also. So hopefully, so they will all be uploaded and the links will be up on Canvas. So that's something. And lecture notes, so I won't have them for every lecture, but if you guys think some particular lecture was particularly hard, let me know. I can write a little bit more notes than what I say in class. Okay, but the slides will always be up. Okay, so slides will always be up on Canvas. Okay, and teaching assistants, we have two of them here, one is not. So, Mahesh, do you guys want to stand up? Okay, so that's, so this is Mahesh Akya. His office hours are Monday between 10 a.m. and noon. And that's Srivatsan. He's also on Friday. Okay. So there's another TA who is not here. And yeah, we should fix that. So his office hours are on Wednesday. So that's something to keep in mind. And each of them has these 2-hour office hours. And there will be parts of the course where I will suggest that you guys, I mean, if you have some problems with background, I will suggest that you guys go to them specifically for that background. Okay, so especially things like data structures and probability and so on. There will be parts of the course where I'll ask you guys to go to some of them. So we'll talk about this. Alright, so any other questions about logistics? Yeah?
Do you know where the TA hours will be held?
Oh yes, so all of these guys, so there is something called a data lab, there's a data group lab. I don't know if you know about it. It's in the CS department. It's it's kind of in the middle of the building on the second floor, on the third floor. So third floor is where all the faculty are, and on the same floor, somewhere in the middle of the building, there's this big lab. Maybe I should write this down. Do you also have an office there?
No.
But it's better to hold your office hours there.
I think to put it up on Canvas, like where we hold the office hours and stuff. Yeah.
But do you have an alternative office?
I usually do it in MED 311.
Okay, yeah. So look out for the office hours. Okay, so both the others have offices in this data lab. Srivatsan probably might hold it in a different place. Okay, so look out for that. Okay, so what about grading? So most of the grade will be, so this is typical for graduate classes. Okay, so most of the grade will be based on homeworks. So there will be 6 homeworks, and depending on how people do, I might take the best 5 out of 6. Okay, so that's something that we will see at the end. Okay, so but for now, assume that you have 6 homeworks and each has like 10% of the grade. And there's a final project, so we'll announce details of the project somewhere around midterm. Okay. So it will be an implementation type project. So it's implementing some of the ideas we will learn. Okay, and there's also a final exam. And the date and time for this final exam are usually determined by the university, for those of you who don't know. So it's, okay, so I don't know, remember off the top of my head, but I think it is Monday, December 12th. Okay, so it's also there on the Canvas page. So the Canvas page actually has, this is something I should probably point out. So there's more course information that is officially there on this Canvas page. And this has all the logistics and also links to all the policies. This has a final exam date. This is not set by me, this is, okay, it turns out it's December 11th, Monday, and in the same room. So these are usually determined at a course. Anyone have a question? Yeah.
Is there also a midterm exam, or is it just the homework project and final?
No, there's no midterm. Yeah, it's just the homework project. Yeah.
What about your office?
Oh, right. So I was going to give you guys 3 options, so I will come to that. Yeah.
Sorry, so is the final worth 30% and the project worth 10%? Is that correct?
Yeah, so, okay, sorry. It's 2020. I made a mistake here.
Okay.
Okay, so yeah, I was a bit undecided, then I decided to go with 2020. Okay, so what I have on the slides are the correct ones. I will change this. Okay, so any other question? There's a way to. And also there's a lot of policies here. We will discuss some of these in a bit. But the late policy is something you should probably be aware of. So you can submit late, but it's like 10% deduction for every late day. And I'm not super strict about this in the sense that if the deadline is midnight, you submit at 4 AM, it's probably okay. But yes, roughly speaking, there will be a deduction for every day. And also there's very few exceptions. It's only, so there are some university-wide restrictions for which I'm assuming most of you will not qualify. It's for athletes and stuff. And if you have medical reasons, you need to, there could be many. Those are typically for undergrads, and we just realized there are no undergrads. So I'm justified. Alright, so that's the late policy. And we have a bunch of other statements that you should probably just look at to get a sense of what they mean and stuff. Alright, so
Is there a course website outside of Canvas, or is everything going to be on Canvas?
I've contemplated, so if you really want I could have one, but I think this is good enough. This, somehow people seem to prefer having a one spot thing, where you can also submit assignments and stuff. Okay, and right, so the other thing I wanted to mention is that if you guys think you need to brush up on prerequisites, so I've put a couple of links here. So this is actually a basic textbook on algorithms. So I think this is the other textbook by Kleinberg and Darbosh. And these are just links to slides on this, for this textbook. Okay, so if you guys think you don't know much about, some basics like graph search or big O notation, shortest paths, etc., then these are good slides to look at. So some of these we will actually cover, like flows and so forth. But the first 5-6 chapters is something that you should actually be familiar with. Okay, and for discrete math, there's a very cool book by Layton and Lehman. Okay, so that's also available online. So I have a link to this. Okay, and someone was just asking for my office hours. So okay, so I can do it either Tuesday or Thursday afternoons or on Wednesday morning. So how many of you would prefer like after class on Tuesday or Thursday? Like maybe after like a half an hour break. So what about Thursday? Is it equal for you guys, Tuesday and Thursday? Anybody for whom Thursday and Tuesday are not identical? Oh,
Thursday.
preference for Thursdays. Are you okay with Thursday?
No, actually neither of them work for me.
Oh, okay.
I don't want to be the only holdout.
What about Wednesday morning? Okay, so there seems to be, you know what, let's do a split. Okay, so I'll do 1 hour on Wednesday morning, 1 hour on Thursday afternoon. Okay, so there seems to be equal number, an equalish number. So let's do Thursday PM. We'll do 1 to 2 and Wednesday AM. Okay, so these are the two office hours assignments. So, and beyond this, if you really want to meet me, then you can always email me and we can set up an appointment. Okay, so we've gone a bit far. So one thing I've forgotten is emailing me or the TAs. Okay, so contact. So my email you can write to anything, but one thing that I will check specially for the course is my last name dot course @gmail. So I prefer having everything related to courses on one email. So please send it to this, and then I'll have everything in one place. Okay. And for the TAs, I'll actually send you a link for the TAs. So there's a mailing list for which all the TAs need to be signed up. So once that is set up, I will send you guys. Okay, so look for course announcement. Look for announcements on Canvas. Alright, so Anything else that you guys want to ask? Yeah.
There won't be any kind of quizzes throughout the semester.
Yeah, no, so the homeworks are kind of meant like that. Okay. So there's no real quizzes, there's just the final exam. Yeah.
Is there limitations of languages when we do the homework?
So homeworks, you will not need anything, I mean you'll just need LaTeX. But for the final, only for the project you will be doing implementation. So for that, I will give out some limitations if they apply. Usually you will not have. But so the project, the way it will work is that there will be like about 10 projects to choose from. Each will be some kind of an implementation of a bunch of ideas and how you compare, and basically comparing them. Okay. For some of them, it might be nicer to use a particular language. Like you might need to solve a linear program. For that there might be some simple Python code available or something. Okay. But apart from that, you're free to use whatever. Like for something where you might want to solve some eigenvalue computation, maybe MATLAB is nicer. You're welcome to do it in any other thing, but it might just be easier to do it in some language. So that's what we're doing. Alright, so the other thing I probably didn't mention is that, so this time I thought I will just go with a fixed grading rubric. Okay, so I will, I will post this also on Canvas. So what it will be is like, if you get 80% in a bar, you'll get an A kind of a rubric. Okay, so that's, because I think people often have, so because some of the homeworks will be difficult, you might have confusion about, okay, how am I doing in this class? Okay, and this is just meant to get rid of those kind of questions. Okay, so there will be a rubric that I will post on Canvas in the next few days. If I don't do it, please remind me. Okay, and the same goes for anything that I say I will do. If I forget to do it, it's not intentional, and please remind me and I will do it. Okay, so alright. Okay, so this is another important point, which is how you submit your homeworks. So you will see that actually, how many of you have looked at homework 0? Okay, so please take a look at this, and you will get a sense of what are the kind of questions that you would be expected to do in the homeworks. And so if you looked at it, you would have found that most of them are just writing out some kind of proofs. And for that, it turns out it's a very nice, way to write down proofs and mathematical documents, which is LaTeX. So in case, how many of you have never used LaTeX? Okay, good number. So you guys should start homeworks early. Okay. It's not difficult, but it takes a little bit of getting used to. Okay. So start homeworks early, and you will see that you end up with very nice, beautifully typeset documents. Okay, so that's LaTeX. So yeah, so all homeworks must be made in LaTeX and submitted as PDFs. Okay, so that's part of the, and you will realize that at least for all of you first years, this will be a trend in most of the courses you will see in this at the university. Okay, so that's so it's useful to learn. And very often I will have templates available. And yeah, so this is what I was saying. So if you've not used LaTeX before, please start homeworks early. And yeah, so this is an optional thing. So I saw many of you had some concerns about how questions will be graded and so forth. So if you want to get a sense of that, please submit homework 0 this Friday. Okay, by this Friday, and this weekend, you guys will just go over some, at least, we might not grade every question of every student, but for every student we'll try to provide at least 1 or 2 samples of how we will be graded. Okay, so you'll often have questions on what details to write in a proof and so on. So that's, to get a sense of that, you might want to submit.
So this is an optional activity though?
Yeah, this is an optional activity, yeah. Just because some people have concerns. So some people are just very comfortable writing proofs and they don't have to go through this. Okay, so if you just, if you feel that you want a sense of how grading will be done, then this is a good tip. And Yeah, for those who have not used LaTeX, you might also want to look into something called Markdown. That's an easy way to write down documents. Okay, so just look this up and you should be able to find good resources. Okay, so questions on this? So I know there's a lot of material very quickly, but okay, so the final technical thing is collaborations. Okay, so this is a graduate class, so you are allowed to essentially talk to your friends about the problems. Problems will be fairly difficult, so start your homework early. Okay, so, and you can talk to others, but you've got to list all collaborators for every problem. Okay, so this is something very important. So, and also you've got to write down solutions yourself. So you can discuss problems, but you should write down solutions yourself. Okay, so the point is that you understand what's going on, what is being asked, and so on. Okay, so if you find things that are just verbatim the same statements, then you will lose points for that. So that's the intention. And the same with online sources. Okay, so you can look up anything, just write down solutions yourself. Okay, and cite the sources from which you got. Okay, so you will find that algorithms courses are there in every university, so you'll find that a bunch of problems you might be able to find solutions for. Okay, so if so, just cite the sources and write down the solution in your own words. Okay, so that's there's also an official policy for this, and I'll have the slides up so you will see all of these. So any questions on collaboration? Okay, so this also is straightforward. You will see similar things for basically all grad classes. Okay, so what about prerequisites? So I mentioned a little bit earlier. Okay, so but I want to. So there's some gap in what I'm writing in the show. All right, so I expect a little bit of knowledge about basic data structures and algorithms. So for instance, you should know what arrays, lists, and binary search trees are. Okay, so we're going to look at maybe just binary search trees next class, but in general you should know some of the basic data structures, right? Like queues and stacks and so on. Okay, so these are things which you can just pick up immediately also, but it's good to know them because you shouldn't be encountering them for the first time in this class. Okay, so that's my goal. And the same is true for things like the big O notation. So how many of you, so this might be an easy example, right? So if I have, let's say I have the running time of an algorithm, and suppose the input has size n, suppose the running time is this. Okay, so how would you write this in big O notation? Okay, yeah, so we just look at the leading terms as n tends to infinity, right? So that's what we do. So why do you think computer scientists only care about this big O notation for running times?
Because data is huge, data volumes are large.
Okay, so that's one answer. But if the constant is big, then that matters also. Actually, why don't you guys do one at a time? Okay.
Order of growth for the higher order terms. I mean, as the value of n progresses, n square will increase with a huge magnitude compared to n squares.
Okay.
So,
Yeah. So that's one good answer. So.
It provides a useful way to compare different algorithms, right? Comparing an n squared versus an n cubed is a lot easier than comparing big polynomials or even exponentials with each other.
Okay, so these are all correct, so I'm just writing them down. So any other?
For the worst case analysis.
Well, you can do this for even something that's not worst case, right? So you could say, on average, what's the running time? You might still write it in an O notation. Any other? No.
I think the don't care about the exact time of the running, and it just care how much it increases when you increase the size of the problem.
So that's actually what I was going to say, that, I mean, so computational power has been changing with time, right? So in the sense that you have faster computers today and you have various speeds of at which computers run. Okay, so what you want is a measure which is not quite dependent on the machine itself. And writing things in big O notation kind of makes that point very clear. Okay, so it kind of gives this kind of a hardware independence, if you will. Okay, in the sense that suppose I have an algorithm that has like an O of n squared running time, then no matter what computer I run it on, an instance of size n is going to take is going to be 4 times faster than an instance of size 2n. Okay, so and this is true no matter what computer I run it on for n that's big enough. Okay, so that's kind of one of the big reasons we care about this in theory, especially because it's independent of the actual implementation and hardware and stuff like this. Okay, and I also expect people to be familiar with runtime analysis. Okay, so we'll see examples of this next class, because next class is more of details on the background. But if you look at an algorithm, you should be able to figure out what the runtime is. Okay, and homework 1, you will also see problems of this kind. Okay, and usually you express these things in the big O notation. So this we've already answered. And the next prerequisite that we'll need are graphs. Okay, so hopefully none of you think that the one on the left is a graph. When we think of graphs, we always think of something on the right. Okay, so yeah, so these are the kind of graphs we will study in this course. And you are expected to know the basics about graphs, like how you represent graphs on a machine. Right? So how would you represent a graph? Sorry? I hear adjacency list. Any other answer? Oh, matrix. Yes. Yeah. So adjacency list / matrix. Okay, so these are the most common ones. So there could be other ways, but for directed graphs and so on, there could be other ways. Okay, but yeah. So these are the most common, and also. All of you hopefully have seen things like breadth first search and shortest path and so on. So if you've never seen breadth or depth first search, you really should do some background reading. Alright, so again by way of background, so I thought I would ask a few very simple questions. Okay, so this again, if you've taken an algorithms class, these kind of questions should be easy enough. So the first kind of a puzzle is the following. So suppose you have a bunch of integers. Okay, so you have n integers. They are in an array which goes from a0 to an minus 1. Now I give you a number x and I ask you if it's in the array or not. Okay. So, and I also tell you that this array A is sorted in increasing order. Okay. So given an x, I want you to find out if it's in this array. Okay, so how would you do it? Okay, so everybody actually has seen this. So anyone who hasn't seen binary search, feel free to. Okay, this is something you can anyway easily come up with. So how does binary search work?
Divide it from start in the middle. Divide it. Look at the left.
Okay, so you look at the middle element and you ask, okay, is this bigger than x or smaller than x? Okay, if this is bigger than x, okay, so let's look at a n over 2. If this is bigger than x, then where should x lie? I said it's bigger than x. On the left. Okay, so if it's bigger than x, then you've restricted, then you can restrict yourself to this portion of the array, and now you basically recurse on this, right? So now you have a smaller array. Now you can look at the midpoint of that, and you can ask the same question. So does anyone want me to do this in more detail? So this is, we can do it if you want, nothing wrong with it. But yeah, so the point is that after every check, the search space goes down by a factor 2. Okay? So the search space is the portion of the array in which x is likely to lie. So if I've looked at the middle element and if I found that that is bigger than x, then I have eliminated half of the search space. Right? So initially I don't know where x is, it could be anywhere in the array. Now I've restricted to just the first half. And that's basically that. Right? So every time you have the size of the search space. Okay. So how many comparisons does this take, or how many iterations does this algorithm take? And why is that? Maybe one person.
Because you keep dividing by 2.
Okay.
So it's divided by 2 to the power n. So number of computations, how many powers of 2 will it take to reach that number, which is log base 2n?
To reach what?
To reach the full array.
Well, to end up with one element, right? That's what you want to say. Okay. So yeah, so that's exactly how you make this argument. You say that at every iteration the search space reduces to half. If I have a search space of 1, then I can just trivially go and check if that element is equal to x or not. So that's if you want to be very formal about it, that's the base case where you just take a constant amount of time, and every time you just reduce to. Okay. So this is how we'll officially write this. All right. So okay. So unfortunately, this is I didn't plan this very well. So maybe I can erase this. Okay, so, alright, so what I wanted to ask next was, even in this very basic setting, you can kind of ask some interesting questions, right? So what if the numbers are not sorted? Then can you do something? So what would be the running time? If the AIs were not sorted, and you want to find an X. Yeah, so you can't do anything much, right? So you just have to literally go through the full array. So worst case, okay, so PowerPoint crashed. Okay, so this is actually rather unfortunate. I should try to make sure this doesn't happen. So I've lost all the writing that I have done. So because of PowerPoint crashing, so I don't exactly know how to avoid it. But okay, but today there wasn't things that were very sensitive, so it's fine. So, okay, so now what you can ask is, what if the numbers are not sorted? So we just said that worst case, we need O of n. So this, we haven't proved it, but intuitively it's clear, right, that you need Okay, so you can also formally prove this without much effort, but let's not. And what about, so if they're not sorted, this doesn't work. Binary search clearly doesn't work. But would it work if you had some elements that were equal? Like if it was still sorted, but you had equality somewhere? Yeah, just check for, I mean, it's the same. So, okay, so it also works when you have equal elements. And you can ask some interesting questions by saying, okay, what if, they're not exactly sorted, but they're roughly sorted? Does it still work? So you can say things like this. Okay, so that also will not get into. Okay, so I just wanted to give a kind of an example of a homework. So building off this. So suppose so this was some question that I randomly picked up. So suppose you're given a sorted array of n elements. You want to determine if there's an I such that a of I equals I. Okay, so this is again, so a of 1, a of 0 less than a of 1. Okay, and you want to find out if there's an I such that a of I equals I. Yeah.
How would you start a proof that shows that the binary search is optimal? It seems like anything that sort of a maximum entropy sort of proof would immediately sort of say that that you immediately fall onto a more efficient search and say, okay, if these things are distributed with maximum entropy, then there's some structure to them.
Right. So I guess the question he's asking is, can we do better than log n for finding an element when you have a sorted list? That's the question.
Yeah.
Right? So there's a couple of ways to answer this. Okay, so one, just the easy answer is that, so the index that you want to find is lies between 0 and n minus 1. Right? So there's log n bits that you need to write down the answer. And in some sense that you can prove is, so that's the entropy argument that you are referring to. Okay, so in some sense you need at least so many queries, because otherwise you will not have all possible answers. Okay, so your answer could be 0, your answer could be 1, depending on what the input is. Right? So if you were able to do less than so many queries, then there would be two different inputs for which all your queries could result in the same thing, and for those you would have to output the exact same answer. Okay. So that's a formal way of proving this. So I could, so if you guys don't follow, this is somewhat of a tangent, but it's a great question. So I think the question itself you should understand. We've seen one algorithm to find to solve this problem, right? And what he's asking is, could there be a better algorithm? Okay, so can you do it with, let's say, log n number of comparisons, or like log n divided by 100, right? So, and the answer is no, you cannot do this. You need at least log n queries to actually find if a number is in a sorted list. Okay. And what I said just now is a proof, so I mean, we can talk about it offline if you want the details of this. Yeah. So there's another way of showing this also, which is that, which is again based on the same intuition, that if you ask fewer than log n queries, then you won't end up with every possible answer. Okay, so, and there are n possible answers, so I will write this down as a good homework problem for when the situation arises. We'll do a little bit of lower bounds in this class, so when the situation arises, this is a good homework problem. Actually, these kind of questions are interesting because very often coming up with a clever algorithm is something we can do, but proving that something is not possible is actually way harder. Okay, so that's why lower bound questions are usually much harder than just coming up with algorithms. Okay, so coming up with algorithms, okay, it's a creative process, but once you have it, you have it. Right? But for lower bounds, you have to rule out all possible algorithms. All right. So any other questions? Yeah.
Instead of breaking it into 2, I mean, instead of binary search, can we break it into 3? Will
Yeah.
it make it more efficient?
So what will happen if you make it into 3, right? So that's a good point. So you might imagine that, okay, so let's look at these two elements. These are kind of the breaking points, right? So now what exactly will the algorithm be? Would you compare to both of these, or would you just compare to one of them?
Both of them.
So you want to compare x to both of them. So that's good. So you can compare x to both of these guys. So it's a n by 3.
So if it lesser than a by 3, then I will skip the next comparison and I will only take up the first 1/3 of the add.
Yeah. So what your running time? So I can actually do this. So give me 1 second. Okay. So PowerPoint earlier used to allow me to insert a slide. I'm trying to figure out how to do this. Alright, so you have an array and you want to say I look at n by 3 and 2n by 3, and okay, so if I compare with both of these, I can figure out a smaller portion in which I can localize this x. Right? So I have an x and I can make sure it's either here or here. So how would one formally write down the number of comparisons you do here? So I guess you're all saying a recursion of some form.
Yeah,
okay. So let's denote by t of n the number of queries on an array of size n. Right. So now what you're saying is that t of n is 2 plus t of n over 3. Okay, because you do 2 queries up front. Right, so that's what you're doing. So now you can solve this, right? So it's like you get 2 plus t of n over 9 and so on. If you work this out, so you will basically get 2 times log n to the base 3. Okay, because how many iterations will this go to? It is log n to the base 3, right? Because every time you go down by a factor 3. Okay? So after some r steps, it is n by 3 to the r, and if you want this to be equal to 1, then r has to be log n to the base 3. This is equivalent to saying r is. So anyone? Right. So this is the number of 2's that will show up in this calculation. Essentially. Right. So so the overall running time is 2 times log n to the base 3. Yeah.
Why did we do this 2 plus?
What do you mean?
We added the 2.
Yes.
So why?
So because I was counting the number of queries that the algorithm is performed. Right. So I haven't written down the algorithm formally, but what he said is that compare x with a of n by 3 and a of 2n by 3, and appropriately recurse into a subarray. So recurse into appropriate subarray. So the recursion step takes this t of n over 3 because sub-arrays are of size n over 3. Okay. And here we have two different comparisons. Right? So that's why it's 2 plus that. Okay. So this works out with this. And what was the earlier recurrence? Right? So earlier you had 1 plus t of n over 2. Okay, because we were just comparing with one element every step. So earlier old algorithm or vanilla binary search is t of n equals this, which works out to log n to the base 2. Okay. So this one, if you do some calculation, you'll realize that that's actually better than this.
So we don't get to drop that constant term too?
No, you don't get to, because every time you're doing two computations. So that's the trade-off usually in these kind of things. So if you can split into smaller problems, but in some sense, to figure out which problem to go to, you have to spend more work. Okay. So that's the trade-off that comes in these kind of. Okay, so that's very good. Any other?
So is it true for almost every time that we should break everything into 2 halves rather than 3 or small?
Not always. So I mean, there could be cases where picking into 5 is best possible. In fact, in your homeworks, you will see that for multiplication, the more you pick, the better your bound will get. Okay, so you'll see that in your first homework. Okay. That's look out for there's this thing called Toombs algorithm. I don't know if the S is part of the name or not, but okay. So, alright, so that's, you'll see examples of that. Okay, so now we have, now I wanted to look at a slightly different problem. Okay, so now you have a sorted array, again things that are less than one another, and you want to find out if there's an I such that A of I equals I. Okay. So how would you solve this problem based on what you know? And how?
You get to the middle.
Okay.
Let's say 20 elements.
Okay. So let's say it's here A of n over 2. Okay.
Yeah. Suppose it's 20 elements, you get to the 10th index.
Okay.
And if it is 11, at that point if it is 11.
Yeah.
It means that towards the right side it will be increasing. You just leave that and you.
Okay. So you'll have to make that argument a little bit formal. Okay. So it's, I mean it's fine, but how do you say that towards the right it's all bigger than 11? You say that okay, every time it increases by at least 1. Okay. And here there are two things that are actually very important that you should notice. Okay. So if you don't see it immediately, just go back and think about it. Okay, so what we should notice is that it's very important to have integers and to have integer AI, and it's also important to have strictly increasing. Okay, so the earlier problem, it was okay even if you didn't have strictly increasing, right? It was okay to have equality, but here you really need them to be strictly increasing. Okay, so this again, you can try to come up with examples where binary search will not work if you do it. Okay. So this is one way to solve this problem, and you can argue that this kind of works. Okay. There's another sleek way to solve this problem. Anybody?
If we XOR every bit with the
I'll get that. Yeah.
If we XOR every bit
with what?
With the with I with AI.
Okay.
So if it's equal, it will be zeros.
Okay.
And if it's not equal, it will be 1.
Yes. So it won't have all ones, right?
It would, yeah.
Okay. So what?
So you don't want to decide whether lift is increasing or decreasing. You just have a left bound and right bound, and just you want to evaluate the quality that's between left and right.
Well, that's a different way of implementing binary search.
Yeah.
Yeah. Right. Yeah. I mean, I guess it's roughly the same, but I just wanted to say that if you really want to be clever about it, you could always say, suppose if this array is increasing, then you could say that I look at the new array, which is a of I minus I, call this b of I. Now this array is also, it's increasing, but it could have some equal element. Okay, so it's a non-decreasing array. Okay, so this is a b is a non-decreasing array. And note that if I can query I can query b. Query a, I can also query b. Right? Because b of I is just a of I minus I. And now I can just do vanilla binary search on b. Okay. Because we've observed in the previous slide that binary search also works when you have some equalities. Okay. So then all you'll have to show is that this b is non-decreasing. Okay. And that's kind of easy to see, because if a was strictly increasing, then a of a minus I is strictly, it's non-decreasing. So, okay. Yeah. Any questions on this?
You said you do binary search. What are you searching for? Zeros.
Now you search for zeros.
Zeros.
Yeah, because finding zero is like saying, yeah.
So what was the first algorithm explanation? I didn't hear it in the other corner.
Oh, this one?
The very before you said this version.
Oh, the first version. Yeah, so this actually we didn't get into. So what you could do was, so you again look at n over 2th element. Okay, so look at the a of n over 2. Okay, so suppose this was actually bigger than n by 2. Okay, then there's no way anything on the right can be the answer. And the reason for this is that these things are all integers, and they increase by 1 at every step. Okay? So for that reason, it's n over 2 plus, it's a n over 2 plus 1 plus 2 at least, that much. So that's why you can't have something on the right for which a of I equals I. So again, you can reduce this to half. And now you can restrict your search to this. Okay? Now you're going to ask, what if a of n over 2 was less? Then it's not so clear, right? So if a of n over 2 is less, then okay, yeah, then nothing on the left can be the answer, because those would all be strict.
Okay.
So that's the same argument. Yeah.
So practically, we can actually, if we have an array, we can directly look up a of I. So
yeah,
that's constant. That contradicts here. So I think B here has like a logging solution.
Mm-hmm.
But does that mean that the implementation is underneath login, or?
Oh, you mean like hashing and stuff allow you to see membership in constant time? Well, yeah. So that we'll get to that. It's kind of an illusion in the sense that you assume constant word size, in which case the number of things that are available, the number of n, the n is kind of bounded implicitly. Okay, so log n bounded. Yeah.
So the first argument was faster, right? Because here in the second one you have to do n subtractions.
No, so that's the thing. You don't have to literally do the subtraction and build the array.
Yeah.
Because suppose I ask you what b of I is, you can always do it by accessing a, right? You just do a of I minus I.
Yes.
Okay, so that's why both are log n. This is just a cleaner way to write the proof, and it gets to what I was going to say, which is that this kind of reduction between things, right? So if you know an answer to a problem, then it's good if you try to watch out for it. Maybe you can just reduce this problem to that by just a simple observation. Okay, so that's what I want to get. Yeah.
So the question, the fact that it's using I, does that mean it's integers, or because it doesn't explicitly say that it's integers?
Yes, so this is a bad phrasing of the problem. So that's maybe, yeah. So it has to be integers, and they have to be strictly increasing. Yeah, this is actually from this textbook. I don't know if in the textbook it's written so badly, but this is what it assumes.
So if they were not integers, is there a way to do it?
Yeah, so that's going to be one of your homework problems, that you cannot do it. Okay, so if you can do it, you can solve the general problem of I mean, then you can solve the unsorted version of this problem. So, which we just agreed we cannot do, right? Like worst case, we need overfit. So, yeah, so the reason I'm asking these questions is that even for very simple things, you can ask kind of interesting questions around these basic things. So that's what I will demonstrate. Okay, so any other? Okay. So we have about 10 minutes. So I wanted to actually go through one thing which probably is useful for you, which is how you write down algorithms. So many in homeworks and stuff, you'll be asked to write down or come up with an algorithm for a certain problem, right? So let's take a basic example. So this is not what I mean when I say describe an algorithm to do this. Okay, so you don't literally have to write down the code in any particular language. Okay. So it's good to have, assume that you have some basic subroutines, like that is a procedure that tells if an array is sorted or not. And this can be done in linear time. We know it can be done in linear time. Okay, so these kind of basic assumptions you can make. And you can have something like this. Okay, so in this case, it's not very different from the previous algorithm, but it still looks a lot more readable. Okay, and this is what I expect you guys to write down. And this is how you should be thinking when you're coming up with algorithms also. Right? So you just say, okay, so this is a sorting procedure. As long as A is not sorted, go from left to right, see if you can swap neighboring elements. So this is what this algorithm is. So anyone know a name for this?
Bubble?
Yeah, so this is called bubble sort. Okay, so this is what it does. As long as it's not sorted, you do this. And you don't have to literally check whether A is sorted or not. You can do it when you're inside the loop and so on. Okay, but we won't get into that. Alright, but what I wanted to illustrate was that when you're writing down algorithms, and also when you're thinking of algorithms, you should, you should basically, don't think of it as like literally what's going on, isolate into subroutines, kind of think at a high level. Okay, and that's what we would like to see when you're writing up your solutions. Okay, so questions on this? This is arguably a very toy example. So actually I have another slightly trickier example, slightly more involved example, which is, okay, so suppose you have a graph G, and so a graph has vertices and it has edges. So the set of vertices I'm calling V, set of edges I'm calling E. Okay, so that's again standard notation in graphs. Okay, so if you have a graph like this, and this is a procedure which I'm calling Euler. Okay, so actually, how many of you have seen this procedure before? Okay, so there's a good chunk who have not seen it. So these are what are called Euler paths in graphs, and it's a way of basically, I don't know if you guys have seen these puzzles. Like you have a bunch of edges. Like let's say you have a graph like this. Now you want to start somewhere and go through every edge precisely once and return to your starting point. Okay, so that's what's called an Euler tour. And it's named after this famous puzzle in the 1700s, which Euler is not going to solve. Okay, and but the algorithm for solving this turns out to be extremely simple. Okay, so an algorithm is basically you have this graph. Every vertex has some degree, which is just the number of edges that connect to it. Okay, so that's the degree. Degree is, hopefully all of you have seen this degree of a vertex is number of edges incident to this. So again, there's a problem in your homework 0, which asks what is degree and so. Okay, so that's So you find all vertices that have odd degree, and you start at one of them. At every step, you just keep taking an edge that you've not taken before. Okay, so it's a very simple algorithm. You just keep doing this, and I have not taken this edge, and I haven't taken this edge. Maybe I can back like this. Okay. And this process will stop at some point. because you might hit a, actually, when will you stop this process? Sorry? Yeah, maybe you start first.
Once all the edges are
Well, should that always be the case? I mean, would you always visit the edges? I mean,
You might hit an edge where you might hit a node where all vertices have been taken, but there are still some other edges which you can't reach.
Okay, so what he's saying is, this process is very local, right? Every step, you're at a node, you see what edges are there that I have not taken, and you just take one of them. There's no decision making going on. It's just you blindly follow something that you've not taken before, and keep going, right? So you might not have explored the full graph, but you might just end up hitting a vertex where all the edges out of that have been explored. So that's when you're stuck, right? So that's the place where you're stuck. So this loop ends. So when you have loops like this, you always need to be a little bit careful. You should make sure the loop always ends. Okay? So that's one thing you should be careful. And so in this case, you are marking edges as used. Okay? So there's no way this can go on forever, because every edge will be marked used, and in which case this process has to stop. So it ends when you hit a vertex, all of whose edges are used. Okay. And at this point you break out of this loop, and now you check if all the edges are used, in which case all the edges in G are used. Okay. So an example like what he said does not happen, where there are still some unexplored edges, but you just happen to hit a backward. So you check that and then you do this. Okay, so it's not very important to understand this example in full detail, but what you've got to realize is the way in which I've written this pseudocode. Because I didn't literally tell you how to find every odd degree node in the graph. Okay. And I also did not tell you how, maintain an array of used edges and so on. Okay, so I just said, mark this as used, then basically follow the edge and things like that. Okay, so this is the level at which you should write your algorithm. Okay, so that anyone who reads it,
Just more of a logistical question, because there are several packages in LaTeX for writing that help you write pseudocode. Do you recommend any one over the other?
So I always use this algorithmics. I know people who swear by other things, so it's really up to you. Okay, so So actually, for the purposes of this class, you can just make do with what do you call them? These itemized lists, right? Like 1, 2, 3 kind of things. Just enumerate type file. Because we won't have algorithms that are that complicated that you need something specialized about. Okay, but it's nice if you learn these. So
Is the objective of the problem is to find the Euler path for a given graph?
Yes.
So what if I traverse in a different path and it does not end up traversing all the edges?
Yeah, so that's the thing. So we won't, this is not really the point of this, but you can actually show that that can't happen. Okay, so if there is an Euler path, this very basic procedure actually finds it. Okay, and if this procedure does not find it, then there is no Euler path. Okay, so we can talk offline about this. Okay, so that's it's slightly tricky to prove, but it's not very hard. So any other questions? Okay, so I just thought, I don't know if you have time. Actually, the class goes on till 12:10, right? Okay, so maybe I will skip this and come back to this if you have time. Okay, so I wanted to first go through, actually one point I wanted to make is that even simple algorithms like bubble sort, right? So when we think of running time, we always think of a worst case running time. Okay, so we always say, this algorithm has running time O of n squared. But there are, sometimes you may not be interested in the worst case. Okay, so there could be situations in which, you might want to understand, are there inputs where it runs actually faster? Okay, so this is something that, again, you will see in one of the homeworks, in the first homework actually, which is that for bubble sort, can you come up with examples where it actually just takes time O of n? So, and can you actually classify instances where it only takes so much time? So sometimes it's useful to understand this, and sometimes you might say, okay, if I take an average input, or if I take some set of numbers and randomly permute them, then I run bubble sort. Is the runtime going to be significantly faster? So these are questions you should be asking when you, there are problems for which you can actually get faster algorithms by just doing some basic processing like this. Okay, so it's useful to understand what inputs your algorithms runs quickly on, what inputs it runs slow on, and so on. Okay. So we'll see very few examples of this in the class, but this is something that you should have in the back of your mind. Right. So, actually, any questions on this? Because it's an interesting point, and then we'll go to the course outline. Yeah. So before I actually show you the outline, so here's the high-level goals of this class. So I just mentioned this briefly some time ago, but we'll focus on. So this class we'll see a lot of problems, okay, and it's important not to be overwhelmed by it. The goal is to kind of give you a sense of various ways of coming up with algorithms for problems. Okay, so if you see a new problem, you might be able to have like a set of techniques you can use to solve it. Okay, so that's the goal of this class. Okay, so that's the first one. And it's not also that important to understand the details of the specific problems we'll look at. So there are a few exceptions, but in general this is true. It's important to understand the methods or the kind of techniques we are using, right? Like dynamic programming or some kind of probabilistic analysis. So the specific problems we will use them to are not that important. And the other thing is, so the goal of this class is also to make sure you guys can reason about the correctness. Okay? So you want to show that the kind of question that he just asked, right? Like here's an algorithm, it finds some path, right? And the question is, if there is an Euler path, does it always find it? And questions like this. Okay? So we want to always say that whatever procedure we give correctly solves the problem that we want to solve. So sometimes this will be too difficult to achieve, in which case we'll be able to show that, okay, what I return is not exactly the right answer, but it's close enough to the right answer. Okay, so these are called approximation algorithms. We will see some examples of those as well. Okay, so that's about the correctness. And we would also like to be able to understand how you reason about time and space complexity. Okay, so you give an algorithm, you should be able to tell, oh, okay, so this kind of an algorithm, this is how I would analyze it, and here's like the worst case instance. Okay, so you should be able to come up with something, reasoning there. Okay, so you should be able to analyze the time and space complexity. This could get hard for some problems, but very often it will be somewhat easy. So that's, we'll see examples of this. You can literally go line by line usually and figure out how long an algorithm will take. Okay, and yeah, so as I was saying, so this, we'll actually see different types of problems, and part of it is also to tell you how to think about relations between problems. Okay, so it's nice in the sense that we see different types of problems. And finally, we would like to understand what is called intractability. So it's there are problems which we believe we cannot solve efficiently. Okay, so it's good to identify such problems and in some sense figure out when it arises. Okay, so this is, so I just want to show you the list of topics. You should go look at it on Canvas. Right? I know some of you are still contemplating whether you should take this class or not, so just do look at the topics if something sounds like I don't want to sign up for this, then maybe, I mean, you should not, but you know, usually the discussion will be at a relatively elementary level. Okay, so if you have the basic backgrounds that I was saying, then you should be fine. Yeah, if you have questions on background, yeah.
It's actually mentioned in the homework zero that the deadline is on August 31st, but you mentioned Friday.
Yeah, so there is no deadline, it's an optional thing. So the Friday thing is if you want feedback by next week. You can feel free to submit later, but then yeah, we might respond too late for you. Sorry.